Okay, this is the second part of chapter 5. We were talking about covalent bonds, polar bonds, and how to draw a proper Lewis structure. Down here we have two examples of ammonia and water. Okay, uh, you may or may not have seen it like this, but you can, when you draw it, you're just going to draw lines. You don't have to indicate three-dimensionality by using wedged bonds. So drawing it like this is perfectly fine, and drawing water linear like this is also perfectly fine. When you draw the Lewis structures, I just want you to worry about the number of electrons and paying attention to how it should be drawn, representing a good structure, not necessarily three-dimensionality, but it can be indicated here. Like this looks like it's bent, and sure enough, water is bent. And I'll explain later how that is and why that is. And so this means here, these are dashed bonds, and so this one actually goes into the back of the board, and this one comes towards us. Okay, it would probably look better if we switched it. But just in case you see this in the book, okay, so this solid line means this is coming towards us, and this dashed line means it's going into the back of the board. So sometimes when you draw a Lewis structure, you're going to run out of electrons, and you are going to have to make a double bond. And so double bonds are then drawn like this. This is carbon dioxide. It has two double bonds. And so you draw two lines representing 4 electrons, right? And so what you will see, carbon double bonds are only made when needed, and we are about to hit those rules and work a bunch of examples, and then it should all make sense to you at the end of this lecture. So double bonds are common between carbon and nitrogen, and carbon, oxygen, nitrogen, oxygen, sulfur. Those are the ones that can do two double bonds. Triple bonds are likely between carbon and nitrogen, and carbon bonds also make triple bonds. So, but you won't have to remember that. When you need to make a triple bond, you just go ahead and you make one, and I'll give you the rules on how that works. As far as bond energy is concerned, a double bond is stronger than a single bond, and a triple bond is stronger than a double bond. So it's harder to break. You have more forces holding two atoms together. Here's an example, just looking at carbon and carbon. A single bond has, and the energies are in kilojoules per mole. It almost doubles here from a single to a double bond, from 347 to 611. A triple bond, 837 kilojoules per mole. That's a pretty strong bond. When you draw electrons, you have to, hang on, oh, I lost a slide. Okay. Anyway, let's just continue with that. When you draw simple compounds, you must know the skeleton structure. Okay, so I think we should dive right in and follow these rules, and I'll point the skeleton structure out to you. It's really not that difficult. Most importantly, when you start, the first thing you want to do is you want to count the valence electrons. Those are the electrons that give you your skeleton too, right? So if you have water, H2O, you go to the periodic table, you look at the valence electrons. Water, hydrogen has 1 valence electron, so we have 2 times 1, and oxygen is in group 6 valence electrons. So we get a total of 8 electrons. That's what you got to play with, okay? So that you need to do. So then you put the skeleton structure together. You decide on a central atom. In this case, you don't have a choice because hydrogen cannot be the central atom. Hydrogen is always terminal, sticking off with a single bond and no lone pair electrons. So you can assume a single bond to the other atoms, right? So oxygen here is the central atom. Normally what you would do is, if you have like sulfur and carbon and oxygen as choices, you would put the most electropositive in the center, and that's because there's more room towards the outside, and so the more electronegative elements are going to be on the outside because they can draw that cloud towards them. If it was in the center, it would get really condensed and it would bust apart. So the most electropositive usually goes in the center, and I'll point that out as we go. All right, so you write the skeletal structure. So basically assuming a single bond, and with that you have used up 4 valence electrons. And then you have to take the remaining valence electrons. You have 8, you used 4, you have another 4 valence electrons to use. And you spread them around the rest of the structure here, right? So you have this already. You've used up 4 electrons, and you do that by you fill up the octet around the atoms that are remaining. Okay, so hydrogen doesn't need it. Hydrogen just needs 2. It needs a duet. Octet means 8. And all of the metals need 8 electrons in their outer shell. So you have got 4 from sharing. You need 4 more, and so you put them as dots around the central atom, right? So that means you have 8 valence electrons around all of the atoms, and 2 for hydrogen, right? So okay, so let's practice that. I'll give you a formula, and you can always assume that there's a central atom most of the time, not always. Okay, let's do 9 out of 10. Let's go see how this would work, right? So you have, first you count the valence electrons. So carbon has 4. So you have 4 for carbon. Then you have 4 times 1 for hydrogen. And then you have 6 for oxygen. So that's 14 valence electrons. That's what you get to work with, right? And so if you do what I said 9 out of 10 times, and I did say that because I realized this one is an exception already. If you take carbon and you put the 4 hydrogens and then an oxygen, you can't do that. You have made 5 bonds, and that's 10 electrons. And carbon cannot have 10 electrons, so that's just not possible. So it's going to have to be arranged differently, right? All right, so you have carbon and an oxygen, and you then would pretty easily figure out that, okay, hydrogen can only be terminal. It cannot be on this carbon, so it must go on the oxygen. It can be terminal there. Now you've made 5 bonds. You've used up 10 electrons. That means you have 4 more to give. And you want to spread them out, filling up the octet on atoms where it is needed. Hydrogen has 2, all of them full. A single bond to hydrogen means you're done. Carbon has 4 bonds, that's 8 electron. It's done. Oxygen has 2 bonds, 4 electron. It needs 2 more. So you put them here. 1, 2, 3, 4. And you're done. No double bonds. Don't draw double bonds unless you don't have an octet and you have to draw a double bond somehow. Okay? Let's take a look at this one. This is a little weird. It has a -2 charge, right? So we have 2 times sulfur, and sulfur is right below oxygen, so that's 6. But it has a -2 charge, so you have 2 electrons that have been added. So this one has 12 plus the 2, which is 14 valence electrons. Okay, so you take a sulfur and you make a single bond, and that's 2 electrons, which leaves 12. And so you spread the other electrons around it. 3, 4, 5, 6, 7, 8, and I stop because I have 8 on sulfur now, right? So now move on to the next atom, right? So I've used up 8, 9, 10, 11, 12. Done. Oh, 14. Okay, so here's what I did. I counted it wrong. I have 12 to give. I've used up 2 already. So 2, 4, 6, 8, 10, 12. Right? I did start counting total, and I said 1, 2, and I started out by saying 3, 4, 5, 6, 7, 8. Okay. Anyway, so you're done, right? So you have a sulfur, a single bond, and this has an overall negative charge. Okay, so for now you're done. You sometimes put this in the bracket and you put your -2 charge. Now, We're going to come back to this one. This one, once we know more rules and understand a little bit more about bonding, we're going to revise this. We're going to have to change this one, okay? There's something called formal charges and the fact that sulfur can have an expanded octet. But so far, you'd be done because sulfur has 8 electrons. You don't know anything about an expanded octet yet, so we're going to leave that alone. Okay, so we're going to do SO2. I got my slides mixed up a little bit, but there we go. Weird. Okay. All right, so we get SO2. Put the most electropositive in the center. Here it's not very difficult to know that sulfur is going to go. You can take a good educated guess, but we also need to realize that valence electrons here is 18, right? You have 6 times 3 is 18 valence electrons. You spread the other electrons around it. Well, I think I have that projected. Oh my God. Okay, let's do it like this. So we have 4, you stop. 5, 6, 7, 8, 9, 10, I stop. 11, 12, 13, 14, 15, 16, stop. 17, 18, stop. Cannot do anymore. I'd like to put 2 more and then I'd be done, but no, I cannot put 2 anymore, all right? So this is not our final structure. We have 8 electrons here, but only 6 here and 8 here. So we move a lone pair from an atom that has an octet and make a double bond. Now we need to make a double bond. And so this changes into, and it doesn't matter whether you do it on this oxygen or on this oxygen. So now we have a double bond. We have 4 electrons here, a lone pair on sulfur, and 3 lone pairs on oxygen. And if you're not sure, you count 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 18. 9 pairs, 18 electrons. This is good. Everything has an octet. 8, 8, and 8. So no big deal. And sorry about that. Okay. Moving on to COBr2. Carbon has 4. Oxygen has 6. And bromine has 7. Okay. So that's 14 plus 6 is 20. That's 24 valence electrons. You put the carbon in the center, and then you draw single bonds to the remaining atoms. Oops. All right. That's 6. And then I'm going to put in the electrons from the outside to the inside. All right. So I can start anywhere oxygen or bromine. So I've got 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And so all of the outside atoms have 8 electrons, but the carbon does not. So you have to make a double bond. And then the rule about bromine not making double bonds comes in handy, okay? Oxygen is more likely to make a double bond. So 2 electrons are moved over to make a double bond. Carbon, bromine, oxygen, 4 electrons, and then each of these bromines has 8 electrons. 5, 6, 6, 8 total. 3 lone pairs, 6 6 electrons and 1 from the bond. That's 8. Okay, bromine will only make double bonds when it's the central atom, and it can be the central atom with, in fact, all of the halides. Fluorine will never do that, but there are compounds ClO3 and BrO4 minus, where bromine is the central atom, chlorine is the central atom. So if halogens are central atoms and they're bound to oxygen, they can actually form double bonds. Fluorine will never make a double bond. Okay, it's always going to be terminal and singly bonded. And then, yes, and they can also be bound to themselves, as we will see. Here's another example, HNO3. We have 1 for hydrogen, 5 for nitrogen, and 3 times oxygen, which is 6, is 18. So that's 18 plus 6, which is 24 valence electrons. I'm going to put the nitrogen in the center, and I'm going to have an oxygen and an oxygen and an oxygen. And yes, you can put a hydrogen there on the center, but you're going to run into trouble, right? So I'm going to save us the trouble, and I'm going to put the hydrogen there. Okay? All right, so I have used up 8, and now I will go from outside to inside. Hydrogen is done. So I go to this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I need 16. What do I have? 16 and 8. Yeah, this is not good. 16 and 8. Yes, 24. So I'm done. Okay. So I need to stop. So I have to make a double bond. So I can do that here or from the other side, right? So it's going to look like this. I have 1, double bond it. Let's make sure I have enough electrons here. And as I said, there's a Lewis structure lab that you should definitely practice. Hydrogen. And so this is it. Okay? So no lone pair on nitrogen. And it's a lot easier to do this route than it would be to draw the individual atoms and then try to connect it. So consider that you have a total number of 24 electrons, and it really doesn't matter how you arrange them, okay, as long as it works out in the end. Okay, so we have something also called resonance, right? So for the last 2 examples, we had a choice, right? Here we had a choice. Well, do we draw the double bond between these 2, or do we draw between those 2? Well, both of them are valid. Same with here. Do we draw, well, no, not this one, but the one before that here, right? So we draw the double bond here or here. Well, both forms are allowed, both forms are equal, and those with respect to each other are called resonance structures. Okay, so here we have an example of where the double bond is either up, I'm going to just for the sake of argument call this up and this to the side, can be between the carbon and the oxygen that's up, or the carbon and the oxygen that's to the side. And so the reality actually means that these 2 are switching back and forth. That bond, that extra bond, is going to switch back and forth. Actually, it is this lone pair that's going to go back here, and that's going to go back up. And so this goes back and forth all the time, right? And that has to do with the next concept I'm going to talk about, which is the formal charge. So we'll come back to that one as well. Let's do one more example, and maybe we'll take another break, okay? So we'll do carbon. That's carbonate here, right? So we have carbon, which is 4 plus 3 times 6, and then you have to add this charge, right? So you have, that means 2 electrons have been added. So that's plus 2. So we have 24 valence electrons. Put the carbon in the center. Take those 3 oxygens. Use up 6. Put the rest around it. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Stop. Again, we are just deficient here. We can make a double bond between any of these oxygens. So we actually get 3 resonance structures. Okay? So this is one of them. And just before I stop, as a review, the reason we are done is because every atom here has an octet. And it has an octet because every atom gets to count the shared electrons from the bonds and the lone pairs, right? This oxygen that I circled has 4 lone pair electrons and 4 bonded electrons, or 2 bonds, right? That's 8 electrons. That's exactly what we want. This carbon here has no lone pairs, but it has 4 bonds, and so that's 8 electrons. And then each of these oxygens has 6 lone pair electrons and a bond, which is 2, so they each of these have 8. And so this is what you want to do. You want to make sure that you don't under or overuse the number of valence electrons, and that you always have an octet when you're done, okay, until we hit the formal charges. All right, I'm going to stop this lecture, and it's only been 40 minutes, lecture 1 and lecture 2. You might as well watch another one, right? So see you in about 3 seconds.